Hello, and welcome to From Nand to Dinner, and it's Summer Night's Talk for Clojure European Summertime, August 2020. So, we don't have a lot of time, so I will just jump right into it. So, ever since this whole hey people, let's all stay at home started, I've been getting into hardware and electronics recently. This is what this talk is mostly going to be about. It's a little bit a mishmash of a couple of things I found interesting. A little disclaimer, it has really nothing to do with Clojure, except for maybe this tweet that I think first saw on a slide at a Clojure conference, which is kind of it kickstarts this off a little bit. So it's a tweet by @DaisyOwl that says, if you ever code something that feels like a hack, but it works, just remember that the CPU is literally a rock that we tricked into thinking. So I went, how do we trick a rock into thinking? How does this even work? So I fell into this little bit of a rabbit hole that I want to talk to you about. I call it the tale of semiconductors. So I think the first time I heard semiconductors was in school. So it's oh yeah, semiconductors, super important for electronics, but why exactly is that? And to really understand what's happening, we need to talk about our favorite semiconductor, which is obviously silicon, here in this beautiful crystallized shape. And silicon is actually really cool. What makes silicon so cool? I'm glad that you asked. So for this, we need to go down to the chemical molecular level. And so the element of silicon has 4 electrons in its outer shell. So the outer shell is called the valence shell, and the valence shell is usually trying to hold up to 8 electrons. This is when it's the shell is saturated, it's full, and silicon has 4. This is kind of practical because together with other silicon atoms, it can form very strong bonds because it could always share electrons with its neighbors. So with 4 neighbors, they can share enough electrons to fill up the 8 electrons in the valence shell, and they form this very strong bond. It's very tight. So that's good for silicon. The thing is that, as the name maybe suggested, semiconductor is that it's not it's not a material that conducts well on metals like copper or something. But it still it conducts better than an insulator like glass or rubber. So we are kind of in the semi state. And this is super useful for us because at this state we can tinker with silicon. We can introduce purities into so we saw this grid of just silicon atoms, and we can fiddle with it. It's actually called doping. So we can dope our silicon, for example, with phosphorus. Phosphorus is an element that has 5 electrons in its valence shell. So we have a little single electron extra that we could use. This type of doping is called n-type doping, because we have basically one negatively charged electron at our disposal. But you could also dope silicon with boron, which only has 3 valence electrons in its outer shell, which would kind of introduce a gap. And this is called p-type because p is for this basically positively charged gap. So imagine the gap moving around there's a little hole that's moving where an electron could sit. And this is the fundamental chemical thing that we need to understand if we want to understand how we trick sand or rocks into thinking. But you might be thinking, okay, so now what? We have doped silicon. What's so cool about that? But with this technology and with this knowledge, we can build a transistor. And the transistor is kind of the fundamental, single most important electrical piece that enables all of modern electronics. It's in your phones, it's in your computer, it's in your watch, it's in your whatever. It's kind of logic. It's really everywhere. But also in your toaster or fire detector or whatever. Here's a little kind of so this is the symbol for transistor in a electronic schema. So it usually has this 3 legs. It's kind of important. Here, in the schematic way, in the electronics way, it's called they're called the base collector and emitter. We'll talk about the 3 legs a little bit later. And if you're into home electronics, your transistor might look like this. I also have another one that's a little bit smaller, like this. Whoop. But really, like if we're talking about transistors as like in a computer CPU or something, they are tiny, teeny tiny. We're like talking nanometers here. This is why like a transistor, like in your phone is like probably 2 billion transistors in it. But it's all the principle is the same. But what is this principle, and what does silicon have to do with it? Let's see. So the transistors that I just showed you are also sometimes called MOSFET or MOS transistors, and this is really like it's the type of transistor that we use. That is the transistor that we use today. It's what mostly we just call a transistor. And MOSFET stands for metal oxide semiconductor field effect transistor. So it's actually kind of like a special type, but it's really the only one that is widely used today. And we will actually find out what all these long words that make up this MOSFET word really mean. So we already have the semiconductor, that is our doped silicon, and we also like get to know the rest. But I want to like show like a little bit of history as well, because I think it's really interesting how this tiny piece of technology really like changed the world. So what is even a transistor? What is a MOSFET? What does it do? It's actually like a switch. It can have like an on and off state. The cool thing is though that it has like no mechanical moving parts. So if you have like a switch that is like a button that you need to press, or like a lever, there's something that needs to like mechanically move, so it takes up space and you need a force that's like working on it. But a transistor really is just like an electronical switch. So you can like just through like pulling in the signal or like turning off the signal, you can like change the state of the switch. And this is huge. Another use case for a transistor is actually an amplifier. So if you have like a big, like hi-fi, stereo, whatever, music device at home, there's probably also like a lot of transistors in there just to amplify signals and make it really loud. But this is not what we're focusing on. We're focusing on the switch part. The field effect in the field effect transistor, like the idea that we will get to know, was actually originally proposed in 1925, but it was just an idea without any like working device. This is a little bit of a shame because it was patented, and only after this patent ran out 17 years later. So it was like 17 years of just like waiting until like you could use this for free without having to pay licenses. Also like probably world wars, but you know, that's how it goes. And then after this like period of like doing nothing, people started working again. It was like because this could really like change electronics. And in 1959 at Bell Labs, people developed like the first MOSFET transistor, basically the same thing that we still use today. It changed everything. It kickstarted the information age revolution. And how did it do that? How just like a little like silicone thing changed everything? And the cool thing is that transistors were able to replace vacuum tubes in computers. So this is actually a photo of a radio, but since like transistors are now used everything, like previously you had to use vacuum tubes. And vacuum tubes are these the light bulby things like that you can see in the back. And you have to imagine that, like, you know, when we think of like old computers in the 50s or like 40s, 50s, we like think of these computers that filled entire rooms. And the reason why they filled rooms is that they had to fit a lot of these vacuum tubes, like tens of thousands of vacuum tubes that couldn't, like for the chemical purposes, like the chemical reactions that happened within them, they couldn't be made much smaller. The also problem was that they were bulky. They burned through easily, so they had to constantly be replaced. It was just a hassle. But this is the only thing that existed up until this point. And once these tiny transistors were made, like they were really like the first generation even was so small that it just drastically changed the size the computers had to have for them to work and to do all these computations. And they're still getting smaller. Connected to this, you're probably aware of Moore's law, that like the number of transistors like doubles every year, like every 2 years. And this was true up until like recently, where we're now like ending this period of doubling, since we're kind of like at the end of what's physically possible for this MOSFET to work, or like how it works, and we'll see why. Okay, enough like historical parts. Let's go back to the MOS transistor. So how does it work? How does it really work? So I drew this picture here. And this is really nice. So this is basically a look inside the transistor. the lower part that is called N and P and N, this is the silicon wafer. So this is really just like a very small layer of silicon, and N and P are the doped regions. So we learned that N-doped silicon is doped with phosphorus, so we have like a surplus of electrons here, and on the other side, and in the middle we have P-type silicon, so with boron, so we have a gap, like an electron gap. There's not enough. Okay, what else do we have? So we see that both N-type regions are divided by this P layer, so there's no direct connection. We talk about that in a second. The other important part is that both N-type regions are connected to the rest of the circuit. So if you like think about like in the finished transistor, we have like 3 legs. One is connected with called source, or like earlier we had like a base collector and emitter, and here they're called source, drain, and gate. So imagine that in our circuit, what we ultimately want is to have a switch that goes from the source to the drain, and then we can switch on and off by putting a voltage onto the gate. So what we see right now is that the switch to the transistor is turned off. So there's no electrons running from the source to the drain. Why is that? And this has to do with this thing that is labeled depletion layer. So the interesting part is that really on the border from the N-type dope to the P-type dope region, the surplus of electrons on the N-type will move over to and fill the gaps in the P-type region. But this is just on this very thin border in between the regions that will like kind of like have a field effect that acts as a border for more other electrons to move. So like you would have to exercise a great force to like move more electrons, and they naturally don't do this. So in this depletion layer, it acts as a barrier for more electrons to like just naturally move. So the transistor or the switch is turned off. The interesting part is now what happens in the next step. It has to do with the gate. And the gate is a metal plate, M, that is insulated from the silicon through an oxide layer, O. And yeah, then we have the semiconductor layer. So this is the MOS type. We have a metal oxide and then the semiconductor, our silicon. And the interesting thing is if you now put a voltage onto this gate, so you have a positive voltage here, this will exert an electrical like field very close to the border here, where through the insulated area in the silicon. So like only very close to where only very close to where we have this field effect, so where the positive voltage is at. So it's not super powerful, but it's definitely powerful enough to create a field effect that breaks down these barriers from the N to the P-type region, and it makes it possible that then electrons can move from the source through this like broken down barrier into the drain. And once like immediately when you remove the voltage from the gate, this barrier is like erected again, the natural depletion layer like build their barriers up again and switches off. So you can switch these things super fast, and you really don't need a lot of space for this to work. So it's really just like a play with some physical properties and like some chemical properties for this to work. And this is how a transistor works, basically. I find this is super fascinating because it really is kind of like a hack. How can you use like normal like electronic field effects to like get this thing to work the way you want it? And from here on out, now we have a working transistor, and this is really like the building blocks of everything in electronics. So we have current or no current, which is the two states that we know as binary. It's like true or false, 0 and 1. And then with transistors, we can build things that then connect as like logical operators for like Boolean algebra, for example. So like popular gates, like the fundamental gates are not and or. That we can put together in certain logic to create like more sophisticated gates like Nand, NOR, exclusive OR, and not exclusive OR. And these we can then like put together to build half adders and then full adders to like start doing computation, like counting numbers together. And from that, we can build an ALU, like an arithmetic and logic unit. We can build memory, like circuits that remember a state. This is like, it's really blowing my mind. And as you put more of these things together, you actually get a CPU, which is usually then doing all the computation that we usually program with. And this is just like, oh my God, like just imagining that all of this like technology was built in such a short amount of time in the 20th century is just like mind-bending to me. However, I will not go further into this because this is like, there's so much to talk about and in way more detail than I can explain. You probably, or like maybe you've heard of the book that's called From Nand to Tetris, which is also part of my talk title, I guess, where this is really like going from this NAND gate that I like shortly mentioned to like how to rebuild a CPU and then program, like make a programming or something that lets us play Tetris on the CPU. There's also like a video playlist that goes until like how to build a CPU. It doesn't have the Tetris part, but maybe if you're more into watching videos instead of like reading a book, this might be more for you. For the rest of the time, I want to like shift the focus to another protagonist that is called exclusive OR. And this is a schematic of like how many transistors do you need to actually make an exclusive OR gate. In this schematic, it uses 6, I think. So there's 6 transistors in an exclusive OR gate. Usually it's just like abstracted into the symbol, which is like the OR like spaceship symbol with like an extra little bow at the end. And the cool thing is so like all of these gates have these like little truth tables, so you can see like you have 2 input signals and an output signal, and what is it that you expect. So an exclusive OR is basically the same as a normal OR, except that when you have like both input signals are true, you get in a normal OR you get also true, in an exclusive OR you get false. And this brings us to part 2 of this talk, which is dinner with cryptographers. So this is all about the dining cryptographers problem, which is like a problem that I stumbled upon some time ago. And I will just read it to you as it like is described on Wikipedia. 3 cryptographers gather around a table for dinner. The waiter informs them that the meal has been paid for by someone who could be one of the cryptographers or the National Security Agency, the NSA. The cryptographers respect each other's right to make an anonymous payment, but want to find out whether the NSA paid. So I guess that's what you do as cryptographers. You decide to execute a 2-stage protocol. In the first stage, every 2 cryptographers establish a shared bond-bit secret, say by tossing a coin behind a menu so that only 2 cryptographers see the outcome in turn for each 2 cryptographers. Suppose, for example, that after the coin tossing, cryptographers A and B share secret bit 1, A and C share secret bit 0, and B and C share secret bit 1 as well. Since this is like gets a little abstract quite fast, I prepared a little video to show like what this is all about. So I have 2 cryptographers, they're having pizza. Cryptographers A and B share secret bit 1, A and C shares bit 0, and B and C share secret 1 as well. And this is all this is about. Like there could be like time costing or something that generates like simply a value, like random value between 1 and 2. Okay. Next is the second stage. In the second stage, each cryptographer publicly announces a bit, which is, if they didn't pay for the meal, the exclusive OR of the 2 shared secrets, of the 2 shared bits they hold with their 2 neighbors. On the other hand, if they did pay for the meal, they announce the opposite of that. Okay, so let's go through our example. Supposing none of the cryptographers paid, then A announces 1, B announces 0, and C announces 1. I'll have a little video of that to make this a little clearer. So the exclusive OR of 1 and 0 is 1. And then the exclusive OR of 1 and 1 is 0, because it's not regular OR, it's an exclusive OR. And 1 and 0 is 1 again. If we now take these like publicly 3 announced bits, we like basically compute the compound XOR, and in this case we get a 0. And this is already like the end actually. So this is about like when A paid, which we're going to do in a second. The 3 publicly announced bits combined reveal the answer to the question. One computes the XOR of the 3 bits announced. This is what we already did, or what we already saw in the video. If the result is 0, as it was, none of the cryptographers paid, and then the NSA paid for them. Creepy. Otherwise, if one of the cryptographers paid, they know there was someone from the group, but the identity remains a secret. So I'm going to show you also a video of the second case. So let's say A paid. So usually A would announce 1, but since A paid, we will flip this to the other side. So instead of 1, A will announce 0 in this case. And then if we compute this, we have 0, 0, and 1, which is then equals for 1, which means one of them paid, one of the group. And the first time I read about this, I was what? How can this work? This is magic. But it's really just a super simple protocol to figure out basically integrity, but also remain anonymous in network. And I thought this is so cool. And this is obviously not just a little anecdote story that I can tell you, but this is basically the basis of something that's called DC networks, dynamic cryptography networks, which are, as you may have guessed, anonymous communication networks with unconditional sender and recipient untraceability. So what I think is it's so simple that I could explain it to you with some Lego, and it's also elegant, super elegant, and it's there's still a lot of research being done around dynamic cryptography networks because the problem as it is solved in the story is obviously very simplified. There's no hints at what you do with the shortcomings, which is collisions, for example. What if 2 cryptographers paid? If there are disruptions with malicious messages, what if someone lies? There's someone in your group who you don't really trust, and they just keep spamming you with wrong messages. And also complexity, if your network grows and grows and grows, and you have a lot of participants, computation-wise, and everybody has to share these secrets. Is this gonna last? And there's all this other stuff that people think about. So there's a couple of papers how you actually go about programming your own DC network. There's also papers on different networks that try to actually solve some of these problems that arise if you use this. They have interesting names like verdict and descent and herbivore. But I'm not gonna go into much detail about this because I actually think dynamic cryptographers solve the real life problem quite elegantly. So you don't even need to go so far as to build your own communication network. Because I think it's the situation that you go out for drinks or something, and then somebody paid your tab for you, and you're okay, was this one of my friends, or was it some super creepy rando at the bar? Is something that I think could happen. And dynamic cryptography solves this for me, while also respecting everyone's right to make an anonymous payment, which is also a cool thing. So yeah, at the very beginning I said that I was getting into hardware recently, so instead of playing around with this idea of an app that you can use in a bar, I said why not build a device that solves this problem for me? So I did. I built a device for that. Made a little video of that as well. Let's see how it turns out. This is what it looks like currently. It's very much a hardware prototype with a little LCD screen and 3 buttons because I wanted it to work like a Casio watch. I'm still waiting for smaller parts so I can actually make it a little wristwatch. So I'm going through the modes here. I have coin toss mode if you don't have a coin because you're absolutely a believer in cashless payments. You might not have a coin. You can from the 2 shared secrets with your neighbors, you can get your personal secret, and you can also in public announce compute the cumulative shared secret for all of you. So let's say okay, and as soon as you have 3 bits inserted, it will tell you if it's you or the NSA, but you can still keep adding, so you might not just be 3 people, you might be 4, 5, 6, 7 people, and the app will also prepare you for that. And with this, I want to leave you saying, maybe don't build an app, build a hardware thing. That was a lot of fun. It also was oh my god, wiring and electronics. It's not my strong suit, but it is a lot of fun. And thank you for listening about random things that I hope you found interesting as well. I'll leave the links up a little bit. I have the code for the presentation and also the code for the device online. And yeah, welcome to like ask any questions and reach out to me. Thank you very much.